So in 5.1, we got this important area under curves fact number 1, which is if you can find the area under a velocity curve between two input values, you can find the distance traveled between those two time values, those two input values. So that gives us the reason that we might care so much to find the area under a curve. Now we just want to get better at it. And then we're going to learn lots of other things you can do once you know it. So you can imagine if I want to find area under a velocity curve, I've been using, in 5.1 we learned to use rectangles or trapezoids to approximate that area if there wasn't already a geometry formula that we knew. And you could change back and forth from LRAM to RRAM to trapezoids to MRAM. And you might get a more accurate answer. You might be able to say something about whether your answer is more accurate. But the only real way to for sure make your answer more accurate is to use more rectangles or trapezoids. So to use more subintervals. Subinterval is the word for how many rectangles or trapezoids we use to make up that total area. So let me just remind you of this moment we had back in semester 1 where we wanted to find the slope of a tangent line. So can you find the slope of a curve at an exact point? We said it was the same problem as figuring out instantaneous velocity. And we had a way to approximate it. We could find the slope of the secant line, change in y over change in x. And then we had this idea. If we let the change in x be smaller, we were going to get a better answer. And then we kept doing that with smaller and smaller delta x's, and then finally we said, why don't we just let that change become infinitely small? And we talked about some notation, this limit notation that we could use to say that we were going to let the distance between the two x values get closer and closer and closer and closer to 0. We're going to take the limit as that change approaches 0. So what do we have here? Right now we're trying to find the area under a curve, and we've pasted a bunch of rectangles under our curve, and we're adding up the areas of the rectangles. Our answer is going to get more accurate if we use more rectangles. So we're going to use more rectangles, and then we decide we should use even more rectangles, and then more and more rectangles, and then finally we say, why don't we just use infinitely many rectangles? So we can do that, but we're going to have to use this limit notation too. So we're going to take the limit as the number of rectangles we use approaches infinity. So this idea, using infinitely thin rectangles to cover up the area under a curve. We have a name for that. That's called a definite integral, and we're going to talk lots more about that. This first box you see right here, we have to talk about it, but you may not panic. It's going to get much better. So let's just do this. Let's pretend this limit part isn't here. This symbol, like the giant letter E, that's the Greek letter symbol, and it means add up a bunch of. And we've been doing that so far. You did that in 5.1. We're going to add up a bunch of height times width. And that height times width is designed to represent the area of a rectangle. So the width of the rectangle, that's a small change in the input value. We get it by subtracting, right, the difference between two input values, the distance across, or the width of the rectangle or the trapezoid. And the height came from taking one of those input values that was on that interval and using it as the input to the function to figure out the f value, the output value, the y value. So this is the height of the rectangle times the width of the rectangle. And it doesn't actually matter. This c sub k, that's just a fancy way of saying it doesn't matter if you use the left endpoint, or you use the right endpoint, or you use the midpoint, or you write a computer program to always pick the tallest or always pick the lowest. You're just going to have to use some input value on that interval and figure out the output value there. We're going to use that as the height of the rectangle. It turns out it doesn't matter which input value you use to get the output value, because we're going to, here, this k, that's like saying, what number rectangle am I on? I'm going to unerase this and go back to what we're really going to say now. We're going to take the limit. We're going to let the number of rectangles become infinite. We're going to use so many rectangles, and they still have to fit over that same interval, right? So that means that we're going to become infinitely thin. And if you think about this, if you have an infinitely thin rectangle, you're going to have, can I use this metaphor for you? Imagine you're going to get down to rectangles that are 1 pixel wide, right? It's not a real thing. It's not a real math thing, but I think you kind of get that idea of a pixel. If you pick a rectangle 1 pixel wide, there's only going to be one input value to choose from. You're going to use the output value for that input. There's only one possible height. So you don't have to be so specific about saying how you're going to choose that input point. Because if your rectangles get thin enough, you're only going to have one output value. So this is what we did in calculus for a while. We wrote this. Every time we needed to find the distance traveled, we made f the velocity curve, the velocity function, and we said, okay, we're going to use infinitely many rectangles, add up their areas to find the area under the curve. It's fine. Turns out we're going to find out that the math isn't so bad afterward, but the notation was clunky. So Leibniz looked at this and he said, okay, we know we're going to want to do this problem over and over again, find the area under this curve between this input value and this input value, and he made up a new notation to say exactly the same thing. All right, it's a little fuzzy on my video, but I think you can see it fine on your handout. This is the notation we use for the definite integral. All this symbol here, I'll read it for you, this here. When I read it, I say the integral from a to b of f of x. And what that means is find the area under the f of x curve between input A and input B. It would be the same as saying, if f were the velocity curve, it would be the same as saying find the distance traveled by a particle traveling with velocity f from time A to time B. So just some important pieces of this notation. This symbol is called the integral symbol. We're going to learn lots more about it. I told you in 5.1 that sort of this second part of calculus is called integral calculus. So it's all about evaluating integrals. A and B are the lower limit A and upper limit B. And this function that's here, in this case it's f of x, that is called the integrand. That's the thing inside the integral. Here, this dx here, that's called the dummy variable. It doesn't matter what letter you use there, as long as the letter you pick here is the same as the variable in your integrand function. And just notice where that comes from. This is going to be key to our deep understanding here. Do you see how this notation morphed into this notation? This symbol still means add up a bunch of, but now it means add up infinitely many of, and there's a product in here. This is a height times a width. A height times a width, just like when we were finding areas of rectangles. But now, instead of, the total distance across our interval divided by the number of rectangles you have to give you delta x, this dx implies that our delta x got smaller and smaller and smaller as I used more and more rectangles until it becomes infinitely small. So this is an infinitely small change in x. But we leave it there because it reminds us what this integral means, which is I'm going to add up a bunch of areas of rectangles. And the area of the rectangle comes from the height times the width. So here's our takeaway. This notation, which we're going to practice using, we're going to use all the rest of calculus, it's just a fancy way of saying find the area under this curve between inputs A and input B. So even though we don't know any extra math from what we knew, a section ago, we still have that ability, which is once we see this notation, if we can make a picture and recognize that area as something from geometry, then we're going to be able to report an answer here. So if I want to find the integral from -2 to 2 of square root of 4 minus x squared dx, that means find the area under the curve, that means between the x-axis and the f function, as the x changes from -2 to +2. And if we can make that picture and recognize the area, all we're going to do is report the area. So this is an example. We had one back in the 5.1 video. 4 minus x squared, that's the function y squared, x squared plus y squared equals 4. That's a circle with origin as the center and 2 as the radius. So if I wanted to sketch that, I'm going to pretend that's a semicircle. Thank you for your indulgence. The picture, the curve that I'm getting is just the top half of the semicircle, because if I really wanted to solve that for y, I'd need a plus or minus square root. So it's the top half of a semicircle whose radius is 2 and whose center is the origin. So here's my semicircle. This tells me I want to find the area of this semicircle. So even though I don't know any more calculus than what this integral means, I can use geometry to find the area. A semicircle is 1/2 of a circle. Area of a circle is pi r squared. I know that here the radius is 2. And so notice here, it worked out because my limits were -2 to +2. That's part of being able to recognize what this shaded shape is. So that's 4 pi over 2, 2 pi. So the answer to this integral is the number 2 pi. It's the number that represents the area in square units under that curve. That means between the curve, the semicircle I drew, and the x-axis.